Imagine you want to grow a thriving plant, but instead of rich, dark soil, you're using like a carefully engineered mix of materials. How does water even move through something like that?
Right, and how do nutrients get to the roots?
Exactly. And what makes one mix work so much better than another? It seems like there are hidden factors at play.
There definitely are.
Welcome to The Deep Dive, the show where we take your pile of information and distill it down to the essential insights. I'm host speaker.
And I'm expert speaker. Great to be diving in today.
With me, as always, is our expert, ready to illuminate these fascinating corners of knowledge.
And our mission for you, the listener, is to really cut through the jargon today. We want to give you a fundamental grasp of how these advanced growing systems actually work.
Yeah, we're going beyond just, listing what's in a potting mix.
Exactly. We want you to understand why those tiny details matter so much for plant health and, honestly, for using resources like water and fertilizer super efficiently.
So you'll get a real shortcut to being well-informed about that hidden world beneath the plants.
We're drawing our insights today from Roni Wallach's work on the physical characteristics of soilless media.
Right, and focusing specifically on how these principles are different from traditional soil physics and what that means for actually using these soilless systems.
If you want to master soilless growing, you really need to get a handle on these core physical properties that dictate how the mixes behave.
Okay, let's start right at the beginning then, the absolute fundamentals. What is a growing medium at its most basic level?
Well, any growing medium, doesn't matter if it's soil or soilless, it's essentially made up of three things.
Okay.
Solid particles, water the aqueous phase, and air the gaseous phase. The real key and the challenge is understanding how these three interact.
Makes sense. So one of the first big concepts we need to get our heads around is bulk density, or BD. What exactly is that? Why is it so foundational?
Bulk density, yeah. It's simply the dry mass of your medium divided by its total volume.
Okay, dry mass per volume.
Think of it like this. You scoop up some dry mix into a measuring cup. How much does that dry stuff weigh? That's basically it. To measure it properly, you'd wet the material, let it settle, or maybe compress it slightly in a container of known volume, then dry it completely in an oven and weigh the dry material.
So it's not just about how heavy the individual ingredients are, like perlite versus peat, but also how they pack together like puzzle pieces.
Exactly right. The arrangement of the particles, the density of each ingredient itself, and any compaction, how much you press it down, all play a big role. And here's something that often trips people up. If you mix particles of very different sizes, you can actually end up with a higher bulk density.
Really? How does that work?
Because the smaller particles can sift down and fill the gaps between the larger ones. This reduces the total amount of empty space, the pore space.
Ah, okay. So less overall porosity.
Less total porosity, yeah.
Yeah.
And that means less capacity to hold water and, crucially, less air-filled space when it drains.
That feels counterintuitive. So a higher bulk density isn't automatically better. Sounds like there's a trade-off.
No, there absolutely is. Bulk density directly impacts what medium you should choose for a specific job.
Like what?
Well, say you're growing tree saplings outdoors. You actually want a higher BD medium, maybe one with sand or even a bit of clay. Why? For stability. It helps anchor the plant against the wind.
Okay, that makes sense. Ballast.
Right. But flip that. Think about high-intensity greenhouse crops, tomatoes, cucumbers, flowers. They get watered really frequently.
Multiple times a day sometimes.
Exactly. For those, you need a low BD medium. If it's too dense, frequent watering can easily lead to waterlogging. Roots get starved of oxygen.
Which is bad news for the plant.
Very bad news. Plus, just practically speaking, low BD media are lighter. They're easier to mix, easier to transport, easier to fill pots with. So you see how BD impacts everything from logistics to root health. It's really fundamental.
Okay, so BD is about the packing, the weight in a given space. What about particle size distribution, PSD? That sounds more like texture.
You've got it. PSD is arguably the most fundamental physical property. It truly defines the medium's texture, the range of particle sizes, and how much of each size is present.
And that influences everything else.
Pretty much. It shapes the internal geometry, the pore network, and how water and air move through it.
Yeah.
When we talk about medium texture, we're really describing PSD as a coarse and gritty or fine and smooth. It's an inherent quality of the material.
You mentioned grading patterns in the outline. What does that tell us, like well-graded versus poorly graded?
Yeah, so a well-graded medium has a nice smooth distribution curve. It means there's a good continuous range of particle sizes.
Okay.
A poorly graded one has a more step-like curve. It indicates distinct groups of particle sizes, almost like it's missing some sizes in between.
Can you give an example?
Sure, some types of, say, volcanic tuff or certain perlites might be poorly graded compared to others that have a more even spread. Now, in soil science, they use PSD to estimate hydraulic properties, like water retention. But that relationship hasn't been studied quite as extensively for soilless media, which often behave differently due to particle shape or internal porosity.
Interesting. Okay, so we've covered the solid bits. Now let's talk about the spaces between the solids. Porosity, that's where the action happens for roots, right? Water and air.
Absolutely vital. Total porosity, TP, is just the total volume percentage taken up by pores, spaces for water and air. It's linked to particle shape, size, and how they pack together. But within that total porosity, it's useful to distinguish effective pore space, the interconnected pores that water can actually flow through from closed pores.
Closed pores, like bubbles trapped inside.
Exactly.
Right.
Like inside particles of perlite or pumice, water can't get in there. And another thing, especially with organic stuff like peat or coir, if they dry out completely, they can become hydrophobic, water repellent. So even when you water, some pores might not get fully saturated because the water just beads up and runs off.
Oh, I've definitely seen that with dry peat moss. It's like trying to wet a dusty raincoat. I thought I was just watering too fast.
It can be that, but it can also be the medium itself developing that water repellency. It's a common issue, and it really underscores why understanding these water interactions is so key.
Makes sense. And within that pore space, the balance between air and water is crucial. Let's talk air-filled porosity, AFP. That's all about oxygen for the roots.
Crucial. AFP is the percentage of the medium's volume that's filled with air after it's been saturated and allowed to drain freely. Roots need oxygen for respiration.
They gotta breathe.
They do. And oxygen availability depends on gas exchange between the medium and the atmosphere, which is directly related to AFP. Higher AFP generally means better aeration. It's inversely related to water content, obviously.
Dave's good target range.
Well, for typical field soils, maybe 10% AFP is seen as a minimum. Most soilless media are designed to have higher AFP, often in the 10–30% range at container capacity. But the optimal AFP isn't fixed. It depends on things like your container size and how often you irrigate. Frequent irrigation means you need higher AFP to avoid drowning the roots.
And you mentioned even if the mix itself has good AFP, you can still have problems.
Yeah, if roots become really dense, especially at the bottom of the container, they can form a mat that impedes drainage and gas exchange right in that zone. Even if the bulk medium is okay, that can lead to poor performance.
So it's not just the amount of pore space, but how it's structured, that 3D network idea. Tell us about pore distribution.
Right, the porous medium is this complex 3D network. The macropores, the larger continuous channels, are super important.
Why is that?
They're the highways for roots to grow into, for gas exchange with the outside air, for water to infiltrate quickly when you irrigate, and for nutrients dissolved in that water to travel. They create favorable spots for roots.
Okay. And then there are concepts like tortuosity and connectivity.
Oh, it's complicated.
They describe the complexity of the paths. Tortuosity is basically how winding the path is. Think of water trying to get from point A to point B. Is it a straight shot or a long, convoluted maze? Higher tortuosity means more resistance to flow.
Got it. Longer path.
And connectivity is about how many independent paths there are between points. Are there lots of routes or just one or two?
It seems like we're still developing the standard language for describing these pores in soilless media specifically.
That's true. There's a lack of standard terminology compared to soil science. But the underlying idea connects back to water retention. The water retention curve, which we'll get to, is essentially a map of the pore size distribution, although that link hasn't been fully exploited for growing substrates yet.
Okay, great transition. Let's dive into liquid gold. Measuring water content seems simple, but it's not just about how much, right? Not at all. You can express water content by mass, like grams of water per gram of dry soil. It's gravimetric. Or by volume, cubic centimeters of water per cubic centimeter of medium, which is often used in practice. Or as degree of saturation, the proportion of pore space filled with water.
Okay, different ways to measure it.
Yeah, and there are direct methods, like ion drying. That's the gold standard for calibration. Simple, relatively cheap.
Right.
But it's labor-intensive, takes a long time, 24, 48 hours, it destroys the sample, and crucially, you can't get real-time measurements. And in fast-draining, soilless media, things change quickly.
So that's a big drawback for irrigation management. What about indirect methods?
That's where things like TDR time domain reflectometry come in. These sensors measure a physical property related to water content, specifically the dielectric constant.
Dielectric constant.
Yeah, basically how well the material stores electrical energy in the electric field. Water has a very high dielectric constant, around 80. Soil minerals are low, like 3 to 5, and air is just 1.
Ah, so the water dominates the signal.
Exactly. That high value for water means the measurement is relatively insensitive to the exact composition of the medium or even salinity to some extent. And the big advantage is TDR is non-destructive and gives you real-time, continuous measurements, absolutely vital for precise irrigation.
Okay, so we can measure how much water is there, but you said earlier just knowing the quantity isn't enough. We need to know how tightly it's held.
Precisely. The affinity with which water is retained is crucial for plant uptake. That brings us to water potential.
Water potential. Explain that.
It's defined as the potential energy of the water in the medium compared to pure free water at a standard reference point. Or think of it as the work needed to pull that water out of the medium. We usually express it in units of pressure like pascals or often kilopascals, kPa, or even centimeters of waterhead.
And what forces contribute to this potential, this holding power?
Well, surface tension is key. Water molecules at an air-water interface pull inwards, creating tension. And then there's the contact angle.
Contact angle.
It describes how water interacts with solid surface. Does it spread out and wet it, low angle, or does it beat up, high angle? If the angle's over 90 degrees, we call the surface hydrophobic water repellent.
Like the dry peat moss example.
Exactly. That hydrophobicity in soils or substrates is often caused by organic compounds coating the particles. It reduces water infiltration, causes uneven wetting, and can lead to water just channeling through cracks instead of wetting the whole volume. Big problem in horticulture, especially with peat or coir that's dried out. Re-wetting them can be really difficult.
So this surface tension also causes capillary rise, right? Water moving up narrow tubes. How does that apply here?
It does, but growing media aren't nice uniform capillary tubes. They're complex networks. So while the principle applies, the simple equations are just approximations. What is very relevant is the concept of air entry value.
Air entry value.
It's the suction, or negative pressure, needed to pull water out of the largest pores and let air in. Coarse textured soilless media typically have very low air entry values, often close to 0. This means they drain very easily, and air can quickly replace the drained water, preventing waterlogging.
Makes sense. Now, total water potential isn't just one thing, is it? You mentioned components.
Right. It's the sum of different potentials. There's gravitational potential, the energy related to height. There's osmotic potential due to dissolved salts or sugars. This lowers the water's energy and is really important for water moving into roots across membranes.
Okay.
And then there's matric potential. This is the big one, related to the medium itself. It results from the adsorptive forces, water sticking to surfaces, and capillary forces holding water in the pores. It's almost always negative, representing tension or suction.
So how do we measure that suction, the matric potential, in practice?
We use devices called tensiometers. The classic one has a porous ceramic cup filled with water connected to a vacuum gauge or a pressure transducer. You bury the cup in the medium. Water moves across the porous cup between the instrument and the medium until the tension inside the tensiometer equals the matric potential outside. Electronic versions give continuous readings.
And they need to be different for soilless media.
Yeah, crucially, tensiometers for soilless culture usually need to have ceramic cups with larger pores and thus lower air entry values themselves. This allows them to respond much faster to the rapid changes in moisture that happen between irrigation cycles in these media compared to the slower changes in field soil. Getting that real-time data is vital.
We saw an example showing matric potential changing in a pot of perlite throughout the day as the plant used water. The tension increased steadily.
Exactly. That shows the dynamic nature of water status in these systems.
Okay, so moving beyond single measurements, you mentioned the water retention curve, the RC. You called it the medium's fingerprint. What does it show us?
The RC is fundamental. It's a graph showing the relationship between the water content of the medium and the matric potential, or suction, holding that water, usually measured under equilibrium conditions. It's key for understanding water availability, how much water the medium holds at different tensions, and for modeling water flow.
How does it work? What does the shape tell us?
As you apply more suction, you pull water out of progressively smaller pores. The shape of the curve tells you about the pore size distribution.
And soilless media have a unique shape.
They really do, compared to typical field soils. They usually have very high water content when saturated, near 0 suction. Then, as you apply just a little suction, The water content drops very sharply over a narrow suction range, maybe up to 25 or 40 centimeters of tension. After that initial sharp drop, the curve flattens out.
Why is that shape important?
That initial steep drop means that even under low suction, a lot of water drains out, creating that crucial air-filled porosity, the AFP we talked about. This is vital for aeration, especially in shallow containers where gravitational drainage is limited. It's very different from the more gradual S-shaped curves typical of many soils.
And you said this difference isn't just about particle size.
Correct. You could have, say, tough particles and sand particles of similar size, but the tough might hold much more water, especially at higher suctions. Why? Because the tough particles themselves have internal microporosity, tiny pores within the particles that sand doesn't have. This drastically changes the RC shape and the total water holding capacity.
So it's complex. How do scientists handle these curves?
They often use mathematical models, like the Van Ganukta model, to describe the RC. These parametric models allow for continuous representation and make it easier to use the RC data in simulations of water flow.
Okay. And then there's hysteresis, the wetting and drying dance. Why is that a complication?
Hysteresis means the RC isn't a single line. It's different depending on whether the medium is wetting up or drying down. At the same level of suction, a medium that's drying will hold more water than one that's wetting.
Why does that happen?
Several reasons. One is the ink bottle effect. Imagine a pore, shaped like an ink bottle, wide body, narrow neck. Water gets trapped inside until the suction is high enough to empty it through the narrow neck. But when wetting, air trapped inside might prevent it from filling completely at the same suction. Also, the contact angle can change between wetting and drying.
And this matters in soilless media.
It's potentially quite important, especially given the frequent wetting and drying cycles, the influence of container boundaries, and the unique textures. But honestly, it's an area that still needs more research to fully quantify its impact in practical soilless cultivation.
Right. Okay, we understand how water is held. Now, how does it move? Let's talk saturated versus unsaturated flow.
Okay. When the medium is fully saturated, all pores filled with water, flow is generally described by Darcy's law. It basically says the flow rate is proportional to the hydraulic gradient, essentially the difference in water pressure or elevation over a distance, and also proportional to a property called saturated hydraulic conductivity.
So, steeper gradient, faster flow.
Generally, yes. But Darcy's law assumes nice, slow, laminar flow. In very coarse soilless media, especially under irrigation or drainage, flow velocities can get quite high.
And
then the flow can become turbulent, you get eddies, and Darcy's law starts to break down. The relationship between gradient and flow becomes nonlinear. This can happen in things like gravel or coarse perlite.
Okay, that's saturated flow. What about unsaturated flow? That seems more typical for roots.
Absolutely. Most of the time, the medium's unsaturated pores contain both air and water. Here, we talk about unsaturated hydraulic conductivity, usually written as KK describes how easily water moves under unsaturated conditions, and it depends very strongly on the water content or the matrix potential. Critically, K decreases extremely rapidly as the medium dries out. It can drop by several orders of magnitude factors of 1,000, 10,000, or even more as the water content goes down or the suction goes up.
Wow. Why such a dramatic drop?
As the medium dries, the largest pores empty first, taking away the main pathways for flow. Water then has to move through smaller pores and thinner films, which offers much more resistance. This rapid decrease in K is a huge factor in water availability to plants.
Is it hard to measure this unsaturated K?
It is. It's notoriously difficult and time-consuming because it varies so much. There are lab methods, like the steady-state flux control method. But often, scientists use predictive models.
Predictive models. Based on what?
Often based on the water retention curve. Models like MULMs allow you to estimate the unsaturated K curve if you know the RC. These predicted curves clearly show that dramatic drop in K over a narrow suction range in typical soilless media.
So to model the whole picture of water movement, you need to combine these flow principles.
Exactly. That's where the Richards equation comes in. It's a fundamental equation in soil physics and hydrology that couples Darcy's law, extended for unsaturated flow, with the principle of mass conservation. Water doesn't just disappear.
What does it let you do?
It allows you to simulate how water content or matrix potential changes over time and space within the medium. You need to define the hydraulic properties, the RC and the K curve, the initial moisture conditions, and the boundary conditions.
Boundary conditions like?
Like irrigation applied at the top surface, free drainage at the bottom, evaporation from the surface, water uptake by roots, or the impermeable walls of a container. It's the core mathematical tool for simulating water dynamics.
That leads perfectly into the practical application, wetting and redistribution within a container. You mentioned 4 stages of weight change after irrigation. Can you walk us through that?
Sure. If you track the weight of a container after you water it, you see a predictable pattern. Stage I is the wetting phase itself. You're adding water, weight goes up to a peak. Stage 2 begins when irrigation stops. This is a period of rapid free drainage from the bottom holes. How long this lasts and how fast it is depends heavily on the medium's hydraulic conductivity and the container height. For something like tuff, this might only be 15-20 minutes.
Pretty quick.
Yeah. Then comes stage 3, a transition phase where the drainage rate slows down dramatically. The rapid gravity-driven flow is mostly done.
And finally,
Stage 4 is where weight loss is dominated by evapotranspiration, mostly plant water uptake, transpiration, if the surface is covered or evaporation is low. The drainage becomes negligible compared to what the plant is using.
and this relates to container capacity, which is like the soilless version of field capacity.
Exactly. Container capacity is the upper limit of water the medium holds after that rapid drainage phase, stage 2, ceases. It represents the readily available water pool right after irrigation. Defining exactly when stage 2 ends and stage 3 begins can be a bit tricky, especially with plants actively taking up water.
How can you pinpoint it?
One practical way is to look at the rate of weight loss on a graph. The point where the steep drainage slope transitions to the much gentler slope dominated by plant uptake is often taken as container capacity. It's a key parameter for irrigation scheduling.
Okay, fantastic. We've covered the medium, the water physics. Now let's bring the plant fully into the picture. How does it actually get the water out? Root water uptake.
Right, this is where it all comes together. Roots are the vital link in what's called the soil-plant atmosphere continuum, or SPAC.
SPAC.
Water moves from the medium into the roots, up the plant's vascular system, xylem, and evaporates from the leaves into the atmosphere, transpiration. Plants lose huge amounts of water this way, so they need to continuously absorb more. And in the confined volume of container, this uptake is even more critical.
Are there different ways roots take up water?
Broadly, yes. There's active or osmotic uptake. This happens mainly when transpiration is low, like at night. Roots can accumulate solutes, creating an osmotic gradient that draws water in, sometimes generating positive root pressure. You might see this as guttation, little water droplets on leaf edges.
Okay.
But when plants are actively transpiring during the day, the dominant mechanism is passive uptake. Water is essentially pulled up the plant.
Pulled? By what?
By the tension, or negative pressure, created by evaporation from the surfaces of cells inside the leaves. This tension extends all the way down the continuous water column in the xylem, right to the roots, pulling water from the substrate. It relies on the cohesive properties of water.
That's amazing. And you mentioned an Ohm's law analogy.
Yeah, it's a useful way to think about it sometimes. The flow rate, transpiration, is like electrical current. It's proportional to the driving force, the water potential difference between the substrate and the atmosphere, and inversely proportional to the total resistance along the path.
So, like current, voltage, resistance.
Exactly. The total resistance includes resistance in the substrate, getting water to the root surface, and resistance within the plant, crossing the root, moving up the xylem.
And which resistance is usually bigger?
Under relatively wet conditions, the substrate resistance is often small compared to the plant resistance, especially the resistance to water entering the root itself. However, this simple steady-state resistive model has limitations because the real system is dynamic and resistances can change.
So modeling root water uptake accurately is tricky.
It is. Estimating effective water availability and uptake rates is challenging. There are different modeling approaches.
Like what?
Some models work at the microscopic scale, considering individual roots as cylinders absorbing water, solving flow equations around them. Gardner's model was an early example, though it often assumed constant hydraulic conductivity, which we know isn't true for soilless media as they dry.
Okay, that's detailed. What about a bigger picture view?
Macroscopic models treat the entire root system's uptake as a sink turn, distributed within the soil volume in the main water flow equation, like the Richards equation. The Fetty's model, for example, uses a reduction function to decrease uptake as the soil dries or gets too wet.
But containers add complexity.
They do. The container walls are impermeable, the volume is limited, and roots often grow unevenly, concentrating near the walls or at the bottom. This non-uniform root distribution and the resulting complex moisture patterns mean simple 1D models often fall short.
So what's a practical alternative to complex modeling?
Often, in container studies, root water uptake is simply inferred from water balance measurements. You measure how much water you add, irrigation, how much drains out, and track the change in container weight or water content using sensors like TDR or tensiometers. The difference over time is largely due to plant uptake.
How can we use that weight data to see uptake in real time? You mentioned noise being an issue.
Right. Knowing the instantaneous transpiration rate is really valuable for dynamic irrigation control, especially in these systems with low water buffering. Continuously weighing the container is a relatively simple and effective way to do this. The momentary uptake rate is just the rate of change, the derivative, of the weight over time during that stage 4 drainage phase.
But the raw data is messy.
Very. If you just differentiate the raw weight data directly, you often get a huge amount of noise that completely obscures the real transpiration pattern.
So what do you do?
You need to apply smoothing techniques to the weight data before differentiating. There are various methods: moving averages, polynomial fitting, or more sophisticated filters like the Savitzky-Golay filter. These clean up the noise while preserving the underlying trend.
And that reveals the true pattern.
Yes, using something like Savitzky-Golay smoothing can give you a much clearer picture of how the plant's transpiration rate changes throughout the day, often closely tracking environmental factors like solar radiation or vapor pressure deficit, VPD.
Interesting. Does the plant take water evenly from the whole pot, or does it prefer certain areas?
It's definitely not uniform. Tensiometers placed at different depths often show that the lower part of the container stays wetter for longer.
Okay.
And plants tend to preferentially extract water where it's most easily available initially. That's often the wetter lower part of the pot. As that region dries and the matrix potential decreases, tension increases, the main zone of water extraction tends to move upwards towards areas where water is still more available. It's sometimes called the moving source phenomenon.
This brings us to a really critical point: balancing water availability in the medium with the demands of the atmosphere. How do we define available water in soilless culture? Is it different from field soil?
It is defined a bit differently, focusing on lower tensions. In field soils, available water is often considered the range between field capacity, maybe -10 or -13 kPa, and permanent wilting point, around -1500 kPa. In soilless culture, because we manage water much more intensively, the focus is on water held at much lower suctions. Terms like easily available water, EAW, might be defined as the water held between, say, 1 kPa and 5 kPa suction, 10-50 centimeter tension. Water buffering capacity, WBC, might be the water between 5 and 10 kPa.
So a much wetter range.
Yes, because we aim to avoid stressing the plants. But here's the crucial insight we touched on earlier. Focusing only on water content or matrix potential isn't enough.
It's the hydraulic conductivity, K.
Exactly. The unsaturated hydraulic conductivity, K, tells you the rate at which the medium can actually supply water to the root surface to meet the plant's transpiration demand.
And that rate can be the limiting factor.
Absolutely. You can have a situation, especially on a hot, sunny day, with high atmospheric demand, high VPD, where the medium still holds a reasonable amount of water, maybe at a metric potential that doesn't seem too stressful, like -5 or -10 kPa.
Yeah.
But if the K at that potential is too low, the medium simply cannot deliver water to the roots fast enough to keep up with transpiration. The plant experiences water stress, leaves may wilt, stomata close, and growth suffers, even though there's technically available water in the pot.
So the mobility of the water is paramount.
It really is. It's often more critical than the absolute amount, especially under high-demand conditions.
Can you give those real-world examples again? They really highlighted this.
Sure. The study with roses in tuff versus pumice. Pumice holds less water and has lower K than tuff. In summer, when transpiration demand was high, the tuff-grown roses yielded significantly more, likely because the pumice couldn't supply water fast enough, even with frequent irrigation.
Oh.
And the other one, comparing a standard peat-based UC mix with coir for roses. The coir had better hydraulic properties, especially better K at low tensions, where the UC mix might have become poorly aerated. The result: coir-grown plants had higher transpiration rates and significantly higher flower yield.
So it wasn't just about water holding, but water delivery.
Precisely. Another study looked at roses in perlite under wet versus dry irrigation regimes. The wet regime kept moisture content and metric potential higher. But interestingly, on days with low atmospheric demand, low VPD, the transpiration rates of both treatments were similar, even though the water content was different.
What does that tell us?
It suggests that under low demand, even the drier treatment could supply water fast enough. But during peak demand periods, high VPD, the wet treatment could sustain a higher transpiration rate because its higher water content meant a higher K, allowing faster water delivery. Water becomes fully available only when the medium can supply it at a rate equal to or greater than the potential transpiration demand.
So the big takeaway here is
Hydraulic conductivity is arguably a better indicator of how well a substrate will perform under demanding conditions than just looking at its water retention curve or available water capacity alone. It's about the dynamics of supply meeting demand.
that makes so much sense. Okay, we've thoroughly covered water, but plants need more than just H2O. Let's move into the hidden life of solutes, nutrients, and gases. How do nutrients move in these media?
Right. Solute transport is critical, especially since soilless systems often rely on fertigation delivering nutrients dissolved in the irrigation water. Understanding how those fertilizers move and where they end up is key.
What are the main ways they move?
There are a few key mechanisms. First is advection or convection. That's simply the solute moving along with the bulk flow of water, like leaves carried by a stream.
Okay, carried by the water.
Second is diffusion. This is the net movement of solutes from areas of high concentration to low concentration, driven by random molecular motion. It becomes important when water flow is very slow, allowing concentration gradients to even out. Think of a tea bag slowly coloring the water around it. In porous media, diffusion is slower than in free water because the path is longer and more winding. We account for this with a tortuosity factor.
Makes sense. What else?
Then there's mechanical dispersion. This is spreading caused by variations in water velocity within the pores. Water moves faster in the center of a pore than near the edges, and faster through large pores than small ones. This variation causes solutes to spread out as they move.
So advection, diffusion, dispersion.
And we often combine mechanical dispersion and molecular diffusion into a single term called hydrodynamic dispersion. This is what causes an initially sharp front of solute, like when you first apply fertilizer, to spread out as it moves through the medium. You see this in experiments as breakthrough curves. The solute appears earlier and the peak is broader than you'd expect from pure advection.
Does the substrate structure itself influence the spreading?
Absolutely. Particle size, shape, and aggregation all affect dispersion. For instance, larger particles or aggregates might lead to faster initial breakthrough because of larger pores between them, but also more tailing, slow release of solutes later, because solutes can diffuse into and slowly out of stagnant water within or between the aggregates.
How is this modeled?
The workhorse model is the convection dispersion equation, or CDE. It mathematically combines the advective, convection, and dispersive fluxes, and can also include terms for reactions, like solutes being adsorbed onto the solid phase or being taken up by roots, sourcing terms.
Adsorption, nutrients sticking to the medium.
Yes, solutes can bind to the surfaces of the solid particles. How much binds depends on the solute, the medium, and the concentration. This relationship is described by adsorption isotherms, like linear, Freundlich, or Langmuir isotherms.
And the sticking slows them down.
It does. We quantify this using the retardation factor, R. It tells you how much slower the solute front moves compared to the average water flow velocity due to this adsorption. An R of 2 means that solute moves at half the speed of the water.
You also mentioned non-equilibrium transport earlier. What's that about?
Sometimes the breakthrough curves are asymmetrical or show significant tailing that can't be explained by the standard CDE with equilibrium adsorption. This often points to physical non-equilibrium.
Meaning?
It suggests the water in the pores is divided into two regions, a mobile region where water and solute flows relatively quickly, and an immobile region, like inside aggregates or in dead-end pores where water is stagnant. Solutes had to slowly diffuse between these mobile and immobile regions.
And some media show this more than others.
Yes. Materials with significant internal porosity, like tuff, might show more pronounced non-equilibrium effects compared to simpler materials like sand, affecting how quickly and completely nutrients are flushed or distributed.
So how do we model the uptake of these nutrients by the roots? It's not just about delivery, but the plant actually grabbing them.
Right. Modeling nutrient uptake involves considering both the transport to the root surface, by advection with water uptake and by diffusion down concentration gradients, and the ability of the root itself to absorb the nutrients.
What factors matter there?
Key factors are the root system's characteristics, its size, distribution, growth rate, and physiological absorption capacity, plus the chemical interactions in the medium, like adsorption, precipitation, or mineralization.
Are there different scales of models here too?
Yes. Microscopic models, like the classic Nightinker-Barber model, simulate nutrient movement towards a single idealized cylindrical root. They consider both mass flow convection driven by water uptake, and diffusion driven by the concentration gradient created as the root absorbs nutrients. Often they use enzyme kinetics, like a Michaelis-Menten equation, to describe the rate of nutrient influx at the root surface.
And macroscopic models.
These, again, use a sink term in the overall CDE for the bulk medium. This term represents the uptake by the entire root system within a given volume, allowing simulation of nutrient depletion patterns over space and time within the container.
Are there integrated models that do both water and nutrients?
Yes. Researchers like Heinen and others have developed models that simulate coupled water flow, solute transport, and nutrient uptake in containerized media. These can be powerful tools for exploring things like how irrigation frequency affects nutrient distribution and availability to the plant.
Okay, final piece of this underground puzzle. Gas transport. Roots need to breathe.
Absolutely critical. Medium aeration, specifically the transport of oxygen from the atmosphere down to the root surfaces and the removal of carbon dioxide produced by respiration, is essential for root health and function.
What's the air like inside the substrate? Same as outside?
Not quite. In unsaturated substrates, the gas phase is essentially moist air, but its composition is different. Due to root respiration and microbial activity consuming oxygen and producing carbon dioxide, the oxygen concentration is typically lower and the CO2 concentration higher than in the atmospheric air above.
How does gas movement differ from water movement?
In several key ways. Gas density is much lower than water. Gas viscosity is also much lower, meaning significant gas flow can occur even with very small pressure gradients. But perhaps the biggest difference is in diffusion.
Diffusion?
Gas molecules move much faster than molecules dissolved in water. The molecular diffusion coefficients for gases like oxygen or CO2 in air are about 4 orders of magnitude. That's 10,000 times greater than their diffusion coefficients in water.
Wow, so diffusion is really important for gas.
Hugely important. While some gas movement can happen via convection, bulk flow driven by pressure differences may be caused by temperature changes or barometric pressure shifts, diffusion along concentration gradients is normally considered the dominant mechanism for gas transport in soils and soilless media. Oxygen moves from high concentration atmosphere to low concentration near roots, and CO2 moves the other way.
So we need to understand the effective gas diffusion coefficient.
Yes, DEGS. That coefficient describes how readily gases diffuse through the porous medium's air-filled pore space. It depends strongly on the air content, AFP, and the tortuosity and connectivity of the air-filled pores. It essentially dictates the rate of gas exchange.
Are there models to predict this, Degs?
Numerous models exist, developed mostly for soils. They range from simple empirical relationships based just on air content to more complex models incorporating total porosity or even information from the water retention curve. There are about 6 main groups of these models.
Are they well validated for soilless media?
That's an area needing more work. Many of these models need further testing and validation, specifically for the unique structures and materials used in soilless substrates.
And how would you model gas transport overall?
Similar to solute transport, you could use a mass balance equation. It would primarily focus on the diffusive flux driven by concentration gradients, potentially including a sink term for gas consumption, like oxygen uptake by roots and microbes, or a source term, like CF2 production.
Amazing. We have really gone deep into the physical world of soilless growing media today.
You certainly have.
We've unpacked everything from how bulk density influences container choice to the really subtle physics of water potential and why hydraulic conductivity is often more revealing for plant success than just knowing water content.
We've traced how plants manage to pull water and nutrients out of these engineered environments, the challenges in measuring all this, and finally how gases move to keep those essential roots alive and breathing.
It's clear that the precision needed for top-notch soilless cultivation really comes down to understanding how every single one of these physical properties, pore size, water dynamics, gas exchange, interacts to support the plant.
It's a truly interconnected system. Tinker with one property and you inevitably affect the others.
So here's a final thought to leave you with. Thinking about this incredibly intricate dance of water, air, solids, and nutrients within these artificial root zones, how might mastering these microenvironments not just improve food production here, maybe in tough climates or vertical farms, but could this deep understanding be a key to unlocking sustainable agriculture in even more challenging places, like maybe even off-world colonies someday?
That's a fascinating thought. If we can engineer the perfect root environment from scratch, the possibilities really open up. Definitely something to chew on.